done now?
Yes, I can see it.
Okay.
Okay. So I guess we can start. So first of all, I would like to welcome everyone, all the participants, Prof. Lee and Dr. Gube and everyone. Welcome to the IEEE MMU PES webinar. This webinar is being organized collaboration between IEEE Multimedia University, Power and Energy Society Student Branch Chapter, and IEEE Multimedia University Student Branch, in collaboration with the BV Energy Storage Lab, supervised by Dr. Gubi, and Center for Electric Energy and Automation, and in collaboration with IEEE Malaysia Energy Society chapter. So without further ado, I would like to pass the mic to Dr. Gubi, our advisor and associate professor in the university. Thank you.
Thank you, Hussein. Again, welcome to all the participants and Professor Lee. And I will just take a few minutes just to go through and to introduce Prof. Lee. Professor Lee received the BS and MS degrees from National Taiwan University, Taipei, Taiwan, and the PhD degree from the University of Texas, Arlington in 1978, 1980, 1985, respectively, all in electrical engineering. In 1986, he joined the University of Texas at Arlington, where he is currently a professor of the Electrical Engineering Department and the Director of Energy Systems Research Center. He has involved in many revision of IEEE standards. He is the President-elect of the IEEE Industrial Application Society, IES, and an editor of IEEE Translation on Industrial Application and IES magazine. He is the project manager of IEEE/NFPA collaboration on arc flash phenomena research project. Prof. Lee has been involved in research on many, I think it's a long list here, but I will just name it few. Utility, deregulation, renewable energy, arc flash hazards, electrical safety, smart grid, microgrid, AI, wind capacity forecasting, power quality, distribution automation, power system analysis, energy storage system, infrastructure design, big data, and many more. He has served as a primary investigator or co-PI of over 100 funded research projects with the total amount exceeding $16 million. He has published more than 170 journal papers and 280 conference proceedings. He has provided on-site training courses for power engineers in Panama, China, Taiwan, Korea, Saudi Arabia, Thailand, and Singapore. He has referred numerous technical papers for IEEE, IET, and other professional organizations. Prof. Lee is a fellow of IEEE and registered professional engineers in the state of Texas. So Prof. Lee will be giving us a talk on battery storage technologies and their potential applications in the power systems. So without further ado, I would like to call upon Professor Lee to start his presentation. Thank you, Prof.
Okay.
Back to you.
Good morning and good evening or good afternoon, everybody. And it's kind of interesting when we basically, if you look at my introduction, I do the on-site training, and but now I can add one more credential. It's online training. And so yes, I'm Wei-Jen Lee, and as in the introduction, I'm currently the president-elect of the Industry Application Society. So next time, I would basically encourage that you also establish an IAS student branch chapter in MMU or in other place. Okay, so on that way, then I will be even more than happy to basically provide a seminar. And today, that I would like to talk about the battery storage technology and their potential application in the power systems. As we all know, for the power system, that we always have to do the balancing between the generator and the load, almost second by second, because we try to maintain the voltage and the frequency of the system in order to improve basically secure the reliability and quality of the power supply. But when we look at it here, that also for the electric power infrastructure are changing dramatically around the globe. Okay, so we have seen a lot of system from the original vertically integrated system become a deregulated environment. And also with the technology that basically we also have a lot of renewable energy online. As we know, for the renewable energy, they are intermittent in nature. So with that, become it's a challenging and opportunity for the power system operation, because the renewable energy, as we know, we don't require a fuel cost. However, because of the intermittency in nature and that they are difficult to predict and control, then that poses a very significant challenge for the power quality. So with that, and also the development in the technology side, the battery storage system, and we all consider, because the battery storage system, we used to have one, okay, so you consider energy storage, like a pump storage, and it's a large scale. But for the pump storage, their operation is not that flexible, and their response is not that quick. So yes, they can do a steady state operation. However, if you wanted to do the frequency adjustment or some frequency following or load following, it can be a challenge. So with the development on the battery storage system, we consider this is a game changer, because we have seen, okay, how fast they can respond. They can respond in seconds. So on that way, we consider, okay, if we can put the battery storage system into the system, then that will change all the paradigm, all the platform on the future power system. So when we try to look at a storage system, then we try to determine, okay, what is the power, how much power they can deliver, and what is the energy capacity. Because the power is basically, when you try to look at the energy storage system, then we try to look at it. There are three ratings over there. One is their power rating, how much they can do the exchange. And then the second one is how long they can last. Because yes, you can have a large power, but it only lasts a few seconds or fraction of second. Then you can have some application, but for the long-term operation, that still have some deficiency. And the other one is how fast they can change. Okay, what is the rate of change? And then, so when we try to look at this one here from the functionality point of view, we try to look at the power density. We like to look at the energy density and the RAM rate. And for the other part of the operation is from the economic point of view, from the safety point of view. What you try to look at it, what is the so-called round trip efficiency? You have to charge, discharge. So how much energy you can take it out once you charge it? For example, you charge 1,000 kilowatt hour, and then how much you can take it out? So what's the efficiency? And then the other one is the cycle life. Okay, so you basically, when you put it over there, and then basically how many cycles that you can charge. Because the battery by itself, you're going to look at it. Okay, for the battery, most of you have the car, and the battery has its own life. Okay, so how many years you have to replace the battery. So what will be the cycle life of the battery? And the other one is the calendar life. Calendar life is basically, okay, if you put the battery on shelf, you charge it, and are they going to basically the self-discharge? And also, if you don't use it, how long will it last? Then one very important factor we will consider is the safety of the battery, because the battery, you store all the energy over there. So, and from the design point of view, you try to have a very minimum internal impedance, so you can deliver a lot of power over there instantaneously. So just like when we try to buy a battery for your car, then we always look for the so-called CCA cold cramped amps. So how much amperage that battery can release. So you will have enough power to crank your starter. And this is also the same thing in the energy system, in the power system. We also try to look at it. But on that way, okay, this is the more like it's a double-edged sword. It's basically, you try to crank up, try to release as much as power as possible, as quick as possible. In the meantime, when you have a short circuit, then they are going to release a tremendous of energy that causes a safety hazard. Okay, the other one is also the reliability, and then we also try to look at how does it impact on the environment, because yes, we don't want to solve one problem, okay, on the energy storage side, and then create other problem to the environment. Okay, so these are the basically that when we try to look at the energy storage system, we try to look at it from the supply side, or we try to look at the operation side. And this is the figure from the EPRI report. And you try to look at this one here. This is basically how long. This is more on the energy side, how long they can last. And this side is on the x-axis is how much power they can release. Okay, so on this way here, we like to basically, okay, look at this portion here. You're going to have you have a higher energy density. You also have a high power density. That would be the ideal case for the application on the power system. And of course, right now, okay, there's basically at the time when they created this table, the lithium-ion battery is on this range. And now the lithium-ion battery, we are going to move, okay, make it longer, make it, okay, that basically they can release more energy. So yeah, if you look at it, okay, most recent development, we focus a lot on the lithium-ion battery. And of course, it's basically, we also look at other technology. For example, several years ago, in 2012, that the U.S. Department of Energy put in $120 million for the Argonne National Lab. And what they try to do is they try to look for the energy system beyond the lithium ion. Okay, so because you try to make it lighter, you try to make it higher energy density, they can release power with higher power density. So that's suitable for high power application. And so on that one here, then we try to look at it, all kinds of storage, because when you try to put in the storage system, that here is some of the example here. You can see, okay, you're going to have a residential here. Okay, this part is a residential, and this part is a non-residential, and then okay, front of the other one is we call it the front of the meter. Front of the meter is on the system side, and in the power system, we always refer to it, if it is on the customer side, we always say, okay, this is behind the meter. Okay, so you can see a lot of, okay, recently we see a lot of development over there. Okay, and this is just the Q2. So the Q1 here, and you're going to see, okay, well, it's incomplete information because right now it's the 2020. And if you go online, you're going to see a lot more development recently. And here is one of the example here, and then try to look at it. Okay, what is the development in the United States? And so, yeah, of course, when you try to look at the battery over there on the development side, it will be it's kind of interesting because the definition of the battery play a very important role in the battery storage system deployment. Yeah, for example, we have seen California, because of the photovoltaic, then California PUC, the Public Utility Commission of California, that required utility to install 1.325 gigawatt battery storage system by 2020. And so they consider battery storage system is the system reliability or system performance improvement tool facility. So it's basically installed in the utility system like PG&E, Southern California Edison, and San Diego Gas Electric. So on that one, all the installation can be right into the rate structure. So they will be able to recover the cost from the customer by charging into their bill, into the basically monthly bill. But in Texas, we consider battery storage system is a generator facility. And for the generator facility, in the deregulated environment, the line company are not allowed to install a battery storage because they don't allow to have a generation facility. So on that, the battery storage development is basically rely on the IPP, the independent power producer, and they don't have a guarantee of the return. They can participate in the market, but there's no guarantee on the return. So in other words, in Texas, the development is slower than California. But even with that, I basically recently I talked to my former student who worked at the ERCOT, the Electric Reliability Council of Texas. And he told me, okay, well, actually people find a way to make money or participate in the market. So in 2020, in Texas, we already have more than 100 megawatt. And then it's basically in the near future that they have a lot in the pipeline. So when you try to look at on the technology side, and here I'm just using some example over there, some traditional one. We have a lead acid battery, and yes, we do. Even in the lead acid battery, they do have a lot of improvement. So when you try to look at a cycle life, and normally we don't want to do that. That we will consider the 80% of the type of discharge. Then lead acid battery, the cycling life is about 300 to 3,000. Okay, it really depends on the technology, and their efficiency is about 70 to 90%. And the advantage of the lead acid battery is they are inexpensive, and they are relatively mature technology. And then basically, we already established a very, very comprehensive recycling plan. And its disadvantage is a limited cycling capacity and on the standard type, and they have a relatively low energy density because if you look at the lithium-ion battery, that we normally a typical one is about 200 watt-hour per kilogram, and for the lead acid battery, it's much lower. Okay, and so yes, they do have a lead. They do have a even though we already established the recycling plan, but they still consider environmental hazard. For the lithium-ion battery, it's about 3,000 cycle life, and it's about 75 to 90%. So they have a higher energy density, and they have a lower self-discharging rate. So when you put it over there, once you charge it, it can last a long time. And it doesn't have a memory effect because this is referred to old rechargeable battery like a NiCad battery. And they do have a memory factor. So once if you don't charge it, or if you don't use it up, or you don't recycle it frequently, and then the capacity of the battery will be reduced. And currently, for the lithium-ion battery, they are still relatively expensive. Okay, a couple of years ago, it was about $500 per kilowatt hour. Okay, and right now they try to push it down. Okay, if you look at the power wall from the Tesla, then per kilowatt hour it dropped down to about $350 per kilowatt hour. So people look at it. Okay, if the trend continue, and then the price of the lithium-ion battery can drop down to about 150 kilowatt hour, then that will become very competitive, and then that basically the application will kick off exponentially. Okay, and then for the lithium-ion battery, because they have higher energy density, so that they do have some safety concern. Okay, and then also for the battery by itself, I have seen some of the battery, because several years ago, then for the Samsung cell phone, the self explosion or self ignition, okay, the problem from the battery, and basically they terminated the production line of that type of cell phone. And then also several years ago, even people look at the computer battery for the Sony, and then after the puncture, and it will cause the fire hazard or some explosion. So they do look at it, okay, from the safety point of view. You try to look at the internal thermal runaway or internal charge, fast discharge. Or you also have to look at the external fault. So safety, when you try to use the lithium-ion battery, safety is one of the major concerns. And then the other one is the flow battery. Okay, flow battery, it doesn't require consider, okay, for this one here, okay, they have a higher life cycle, and but they do like for the flow battery, like a sodium sulfur battery, and that basically the disadvantage of this one here is, okay, well, they need a electrolyte tank, and they have a higher maintenance, and then also normally when they operate higher temperature. Okay, and so yes, there are several applications in the United States. We look at it. Okay, some of the flow battery, like in Virginia, they have a sodium sulfur battery, and then in Texas, we also have an example on the sodium sulfur battery. They basically serve a single serve community, so a village. They only have one power line getting to the service area, and then to improve the reliability, they put in the battery storage, the flow battery. So on that one, they can serve, if there's any power interruption, they are able to continue to serve 4 to 8 hours. And then the other one is the supercapacitor. For the supercapacitor, that they do have a higher power density, and their cycling life is high, but they have a lower energy density, because they basically, it's just like any capacitor. Okay, so that they can discharge fast, but it doesn't last long. So when we try to look at application, okay, and on the other one is, okay, when you try to look at how much battery or what kind of battery you should use, it really depends on the application. So when you try to look at the application side, we try to look at it on the transmission level. If you look at the transmission level, then you basically, what we can do is, okay, we can do the upgrade flow, because in the transmission line, you are not going to, if you have a line, okay, 100% is basically 24/7, 100% loaded, then you are in trouble. So a lot of transmission line, you try to look at it, okay, you have a daily load curve. For example, in the daytime, the load pickup, then the transmission loading is going up. At the nighttime, the load dropping, then the transmission line is in the light loading condition. So it's not basically 24/7 with full load. You always have a heavy load, you have a light load condition. And when we try to basically do the transmission planning or try to do the transmission construction, we always try to basically meet the need at the peak. Okay, so if you can do the very simple one, if you can use the storage to do the peak shaving, so you basically drop the peak loading on the transmission line and then shift it to the off-peak period, and then basically transfer the energy before you use it to the location near the load center. Then you will be able to do the construction deferral, or you can do the congestion relief. Because when you look at it, okay, the other one is, okay, when you look at the price of electricity, right now during the deregulation, then we look at the locational marginal price. Locational marginal price is basically, okay, when you don't have any congestion, then every place, the price will be the same. But if your transmission line is congested, then you won't be able to use all this cost generator to support supply the load. Then you will have to use the higher priced generation facility. So on that way, at a different location, you are going to have a different electricity price. That we call it's a locational marginal price, and it's basically caused by the congestion on the line. So on that way, if you can do the congestion relief, then you can avoid using the high price generation facility. And then if the price is good enough, you can do the energy arbitrage. Okay, because it's basically you can do the trading. And for example, in Texas, sometimes the price of electricity can go to negative. So if the price of the electricity go to the negative, then you can charge it, and then during the other time, the price of electricity can go very high. So you can sell it. So on that way, buy and sell, the energy will be buy low, sell high. You will be able to make some profit out of it. And for example, okay, in Texas, that price of the electricity can go up to $9,000 per megawatt hour. So which is $9 per kilowatt hours. And it happened in last year in 2019, August. And the last couple of hours. If at that time you have energy to sell, you can make a fortune. Then the other one is to do the load following, okay? Because I don't know in Malaysia situation, because in the traditional power system we do the capacity charge. But for example, for a manufacturer site or a plant site, they try to use, for example, 10 megawatt, and when they try to apply for the electricity, utility always asks them what would be your peak facility, and then they have to give the number over there, and then normally it will charge $5 to $8 per kilowatt. Consider the capacity. Even they don't use the electricity, they do charge the capacity, the demand charge, and then on that way, if you can reduce the demand charge, then that will be a big saving. So when you do that, you can do the load following, and then also if you have your own generation, then if you can basically curtail the variation or provide the variation through your battery storage system, your generator doesn't have to control, okay, to do the load following, and then the control you can minimize the control requirement of your generation facility. Then you also can improve the power quality. Okay, for example, yes, we talk about the renewable energy. For the renewable energy, you talk about the intermittence, and the intermittence from the renewable energy will cause the voltage variation, will cause the frequency variation, which is cause the power quality problem. So with the battery storage, they can basically counter the variation and then improve the power quality. They also can improve the system reliability. For example, the example used in Texas, they use the battery storage to basically improve the system reliability, okay, reduce the SAFE of the community, and then that you will be able to improve the system reliability. The other one, okay, the last but not the least, is on the ancillary service. Or the ancillary service is basically we consider in the regulated environment. So you can do the regulation, you can do the regulation service. For example, you can do the reg up, reg down, okay, and regulation up, regulation down service, or you basically look at the faster response reserve, okay, frequency, and also the frequency response, okay. So yes, from the regulation service part, then traditional we call it a spinning reserve, okay. When we look at the spinning reserve over there, and traditionally all those reserves come from the generator. The reason why we call it a spinning reserve is, okay, the generator is spinning, and then for the generator, we don't then allow them to produce the full rated capacity. They always reserve something, okay, and to support the system in case there's any incident happen that require more generation facility. So on that way, that basically some of the capacity of the generator was withheld. Okay, so that's the reason why we call it the spinning reserve. And with the development on the smart grid side, then we look at the so-called load participation. Okay, for the load participation side, then the load that would basically come in the so-called demand response. And so also the battery storage system will be able to do that one. So we basically change the spinning reserve to the responsive reserve, okay? And that's basically the new name that people use it in the United States. We don't call it the spinning reserve anymore. We call it the responsive reserve. And because the responsive reserve that basically more mimic the traditional spinning reserve. With the battery storage, like in Texas, we come out a new ancillary service item. We call it the fast responsive reserve. Okay, so because of the battery storage system, response time of the battery storage system is fast, and so they can provide the faster service. And of course, when you can provide a faster service, then the price will be different. So on that way, that gives a favorable consideration of the battery storage system. And then you also can use it as a break start unit, okay, break start service. Historically, we always use the break start unit, and with the battery storage, if they do have enough capacity, they can use as a break start service, and they also can use as a reactive power support. Okay, so yeah, people always use the basically. Okay, so what is the example, and then the latest, the basically not necessarily latest example, the most publicized example is in the South Australia, and it was installed a Tesla's 100 megawatt and the 129 megawatt hour battery. So you can see here, okay, well, of course, if you look at it in detail, they do basically divide it into the different parts, and some with the fast one, some with the slower response. Okay, so but in general, that this is the battery that they install in South Australia, and they already basically, because their response is much far quicker than a coal-fired backup, so they basically provide some improvement in the system. Okay, so that was the big news at that time several years ago. Okay, and it's basically okay. The system they consider the largest lithium battery and put up the test. And well, that it's basically at that time it was the world largest one. At the current situation, okay, the development is in other part of the world, they catch up quick, very fast. Then the other one is, okay, basically, this is the one of the study we did it before, because if you look at it, okay, this is the wind generation output, then they can go up and down very fast. So instead of, okay, well, when we try to look at the battery storage in along with the renewable energy, a lot of people talk about, okay, we can basically store, especially for the wind. Then we'll say, okay, wind blow at the night, and then they basically, okay, they stop at the daytime. And that is almost opposite of the load curve. So a lot of people think about use the battery storages to store the energy at the nighttime and they use in the daytime. And yes, this is possible. This is an ideal case. However, when you try to do this, then the capacity of the battery storage system is enormous, and that may not be feasible economically. So we come out with an idea, say, okay, look at it from the operation point of view. Okay, so how are we going to move from intermittence to become a dependable source? Okay, and if you look at the power system dispatch in the operation room, or when they try to dispatch the system, historically is every 15 minutes. Their deployment cycle is every 15 minutes. Nowadays, people try to drop it down to 5 minutes. Every 5 minutes, like in Texas, they already dropped it from the 15 minutes dispatch cycle to the 5 minutes. So if the wind generation incorporate with the battery storage system, so they will be able to tell for the next 15 cycle, okay, for the next 15 cycle, they are going to give him a fixed output, okay? So basically some certain period of time depends on the size of your battery, then depends on the wind quality, you will be able to tell the system operator for the next 15 or 30 minutes, I can give you this amount. So you turn the intermittence become a dependable source. So on that way, that basically the operator can consider those part of the generation is dependable. Then when they do the economic dispatch, they can exclude that one. And then they can count that one as a dependable source. So that basically will be very beneficial for the system operation. Then this is one of the example. If you use the black start service, so you energize the transmission line, you basically start up the generator, and then once the generator go up, then you can ramp down. So, and then also, to the certain period of time, you will be able to basically recharge your battery back, because the battery storage, remember battery storage system, even those we consider is a generation facility, however, it does need charging. Okay, and if you look at it in the battery storage, as I say, okay, in the ERCA as an example, and so they provide, we call it a fast responding regulation service. Okay, and so you have two terms over there. You consider two situations over there. Okay, so current market implementation, the resource reaches a generation resource when they are injecting the energy to the grid. They consider they are the controllable load. When they are withdrawing, they are charging. They consider this is a controllable load resource. If they are discharging, they are considered a generation resource. So they will be able to put into because on the definition side, they are able to consider, at the present time, they consider that on this one here, consider that is a two row over there. And so in 2017 and 2018, so basically they look at it, okay? So they they do come in with the cap over there. They ask for the 35 megawatt, and with 25 megawatt, that was not awarded. Okay, and of course, if you are not awarded on the service at FRSDN side, then you will be able to use the battery storage for other service. Because if you are interested, you can go to the ERCOT website. They do have a different kinds of service available for the generation facility. So they can do the regulation down, they can do the regulation up. And the 2018, okay, so on the 2018, the cap is still maintained at 35 megawatt. And because they have new, so it's basically they have a new installation on the battery storage. So if you look at it, okay, so in 2018 it's 35 awarded, 25 not awarded. Okay, so total it's about 60 megawatt. And then in the 2018, the total installation is about 80 megawatt. Okay, so and according to the ERCOT, because right now they try to, because as you have seen, okay, in certain place they consider this is a load, in certain place they consider it's a generation facility. So they treat it differently. And so in the near future, they are considering put it together, become one market component. Okay, so this is evolving, and then on that way it become more flexible, and then they will be able to utilize the capacity of the battery extensively. At the distribution level, okay, this is basically okay famous one, the so-called duck curve, because in California they do have a lot of behind the meter photovoltaic PV installation. So during the daytime, that the people come in with the PV here, okay. So and then people go to work. Well, currently the curve is changed, okay, because of everybody works at home, and so they predict that eventually, okay, during the daytime they're going to install so many photovoltaic over there, the consumption is not there, and then at the afternoon time, okay, people go home and after the sunset. So they expect they're going to have about 13,000 megawatt in 3 hours, the ramp. And that basically promote the PUC California that ask the utility company to install 1.325 gigawatt of stored energy by 2020. Okay. And as I say, okay, well, they consider this is the reliability improvement facility, so the expense or the cost of installation will be right into the rate base. And then, of course, in 2018, okay, that because of the wildfire in California, and so PG&E filed bankruptcy in January 2019. Currently, they exercise some precaution. If there's a high speed wind, okay, they realize, okay, well, that basically may cause some wildfire, then they will interrupt the service to the customer. And of course, that causes a lot of trouble to the customer. And then sometimes, okay, the power were out for 2 or 3 days because of the concern. And so with that, a lot of battery storage on the residential area, it's basically popping up. And then also people also consider, okay, should we basically install the community UPS? Okay, and this is for the distribution level. You also can do the upgrade referral. You can do the voltage support. You can do the grid support. And for the community US, like an SNC, they used to have basically, okay, a battery storage under the Piedmont transformer. So on that way, they will be able to support supply the customer. Okay, in some place, if you look at the distribution system, we always try to reduce the SAFE and improve the reliability. But for the distribution system, it's very expensive process if you try to improve the overall system. And however, some of the place that the services are critical. So some of the utility are considering using the community UPS. So for example, put the battery storage under a PEP mount transformer, and then they install the transfer switch. So in case there's a power outage, they will be able to support the customer in need. For example, they have some medical situation, they require continuous power supply. And with that the utility doesn't have to improve the whole site with higher reliability, with their expensive equipment. They can basically do the spot in the reliability improvement. Okay, and the other part is the residential part. Okay, people put in the photovoltaic, put the solar panel over there. So once you put the solar over there, then you consider, okay, yes, that's a base. The price of electricity change. It's a time dependent. It's a location dependent. So you can store the energy while you don't use it, and use it when the price is high. Then that would be beneficial to the customer. It's also beneficial to the utility. So Tesla come out the so-called power wall. Okay, it's a 13.5 kilowatt hour with the 7 kilowatt hour peak to peak power, and so they do have they put out some application over there, and yes, of course, right now the price of the battery storage system is still relatively high. So yeah, I'm looking for the possibility in the future we can reduce it, and you also look at it. Okay, some other company like Samsung or LG or Panasonic, they also have a very similar battery pack, and for the residential usage, especially when people has PV in their house, and then they will be able to self-sustain. And the people talk about the net zero housing, or even we consider net positive building. And so yes, the basically net zero building, it doesn't mean it's a net zero cost. Okay, because as I say, the price of electricity is different. You dump your surplus to the system. When you need it, you bring it back. The price can be different. Okay, so yes, with the battery storage, then you will be able to store the energy, when you don't need it, and use it when the price is high. So you don't sell low, buy high. You can basically just store it. If the efficiency is right, if the cost of the installation is feasible. Okay, and then the other possible application is on the transportation. We always like to have a so-called the transportation electrification, and so that is is driven by we try to look at reduce the greenhouse emission, and this is from the economic sector. Look at it in the United States, on the transportation that produce about 28% of greenhouse gas. It's about the same as electricity. Okay, so a lot of time, people always complain on the electric sector that they produce the greenhouse gas. But if you look at it on the transportation side, they are equally bad. So what they try to look at it is, can we basically reduce the transportation, the greenhouse emission on the transportation side? And so that get into that electric vehicle side. And of course, when you try to use the electric vehicle, if you put an electric vehicle and you charge the electric vehicle with the electricity, people say, the motor has a higher efficiency than internal combustion engine, so you can improve the efficiency. However, on the other side is how green is your electric vehicle? Is they are as green as the power that generated. If the power is generated from coal-fired unit, you basically just transfer your greenhouse gas emission from your the car to the power plant. Okay, so the idea is, okay, can we utilize the energy? Okay, so on that way, so can we fully utilize the renewable energy? And then here is the basically we come out with some idea, say, okay, well, if we can look at it, the renewable energy is your source of variability. And then you try to find a load that will become a source of flexibility. So you can improve the penetration level of the renewable energy. You can utilize fully utilize the renewable energy. So we come out the idea, say, okay, on that way, you can, on the charging side, we consider, okay, if you have a distributed, people talk about V2G, okay, and this is basically the V2G by itself require a lot of more infrastructure because the communication and the location of the vehicle, the willingness of the customer. So this is a lot of, it's not just a pure technical issue, it's also a convenience and the basic social behavior issue. So we try to find out that, okay, a easier way to do it is if you use a battery storage, distributed battery storage, then you basically, it become a multi-purpose. It can be a community UPS. You can participate in the market. You can do the ancillary service, and you can do the battery charging. And then the other one is, okay, well, people also talk about the possibility the battery swap. So you put the battery swap it, then you can swap the battery. Okay. So for example, I'm looking at the battery swap station, and for the battery, they swap the battery. It's about 2 minutes 40 seconds. All right. So on that way, I think it would be much better than you waited the battery station for a couple hours, or you do the fast charging. Okay, at least 30 minutes. So this one here, one of this is one example coming just coming with 2 minutes. Okay, so when you look at the battery side, then you try to look at, as I say, what would be the proper size of the battery. Okay, and it really depends on the application. For example, for the power quality, you need a short duration, and it's basically okay, and it's a localized issue. If you look at the distributed energy storage, then you try to look at hours. Okay, power quality, you're looking for minutes, and for the distributed energy storage, you look at hours, and for the T&D, then that's basically the size. Okay, so you probably need the 10 megawatt, and for the distributed energy storage, you probably hundreds of kilowatt, and for the renewable integration for the large scale, you need a tens of megawatt. And if you try to do the arbitrage, you do the wholesale service, then you try to look at it from the megawatt range depends on what kind of service. If you look at the frequency response, then it's minutes. If you try to do the trading, energy trading, then that requires hours. So it really depends on the application. And then, so every size of the battery has its own application. Just like you get a USB power bank, and it's sufficient for your cell phone. Okay, but if you try to put it into the power system, then it's not enough. So it really depends on the application. How are you going to how to do the application side? And the other one is very important one is, okay, well, I always tell people that when we try to introduce a new technology, it's very difficult to create the trust level. Okay, because it's basically, when there's a new technology, you need to earn the trust from the public, and but it will be very easy to destroy it. Okay, so I always give an example. If an electric vehicle catch fire, it will be in the news. Even if a traditional vehicle catch fire, If it doesn't hurt anybody, then probably doesn't even get onto the news. However, for the electric vehicle catch file, it's a news. And I remember several years ago when Tesla has a electric vehicle cut file in Seattle area, and the next day the stock plunge. Okay, so this is the very important technology. When you try to introduce it, you have to basically, you need a very, very complete, a thorough consideration. You try to look at the different kinds of, okay, the government regulation, government policy, okay, standard regulation. So you try to look at from the component, that the basic, the how are they going to, the basically, okay, the 1642 for the lithium battery, and 1741 is for the inverter converter side, because you have to convert, you have to connect to the system. So from the system component point of view, their performance. And the storage type, then you try to look at the IEEE 1547, okay, how they're going to the interconnection of the distributed resource with electric power system, and then for the system architecture. Okay, so you basically, you try to look at it, okay, you have a, from the component to the system and to the storage installation. Then you are going to have, okay, IEEE C2 or NFPA 70E. So you try to look at it, how are you going to install from the safety or the primary or secondary lithium battery. And then you try to do the commissioning. So what do you have to do for the safety system, how to do the fire protection and the life safety system. Then you try to do the operation and maintenance. Okay, so if you look at it, okay, if you go to the YouTube, and also if you look at some news, and there's a lot of battery storage file in Korea. Okay, so yes, that is going to hinder the deployment of the battery development. And then you also try to look at the incident preparedness, okay, because the battery is a chemical. So you have to look at it. If there's any incident, you have file, you have a spill, and how are you going to handle it? Okay, so it's basically, you need a thorough, comprehensive rule and the regulation to ensure the operation and the installation of battery storage. And then from the storage system, from the safety side, okay, because I'm doing a lot on the safety side, and you try to look at the reliability and aging, and then you try to do the scalability. Okay, so you basically, in the power system application, you use a different type of application, then they are going to have a different scale. And then you try to look at the risk associated the internal fault of the battery, and you also try to look at it external battery. Okay, so when, for example, you have a battery system over there, you connect to the system, then there's a possibility you're going to have a fault happen here, you're going to have a fault happen here. Okay, so when the fault happened here, when you try to look at it, okay, what is the contribution from the battery bank or in your inverter? Normally the inverter will have a small contribution. And if you have a fault happen here, it's an AC system. Fault happen here is a DC system. So they have a different characteristic. Okay. So very, very important one is basically, for example, for the AC, then you're going to see the zero crossing. Okay. So you see the light up and down. So it has a zero crossing over there. And from the protection point of view, with the zero crossing will be a little bit easier. Then you try to look at it. This is for the DC side. Okay, DC side doesn't have a zero cross. Okay, you're not going to have a zero cross. So from the protection, then that would be different. So this, and then also the energy. For example, when you try to look at it, okay, from the personal protection point of view, then we try to look at it, how much energy will it be. Basically, it's going to hurt the people next to it. And for example, on this one here, okay, this is the low energy, and then you just see a fire over there. Okay, But if you depends on the configuration over there, then you come into here. Okay, so if the different configuration, you see the fire shoot at people. Normally, people stand here. For this one here, like people stand here, but the fire shooting down. So this is different configuration, different hazard level. Then you have to do a different type of study. So, and then the other one is, okay, well, then currently I'm working on the DC uprush part, okay, because in the 1584, they are talking about AC. And in the NFPA 70E, they do provide some general guideline, okay, but it doesn't really give a very rigid simulation. They provided some formula over there, but according to a lot of testing, some other simulation, and then they look at it, the result from the 70E, it's over conservative. It has some mismatch. So with the test result. So yeah, currently I'm working with IEEE and then try to work on the DC uprush model. Yes, so for the AC uprush model, I was involved because if you look at my introduction, I was the project manager of the IEEE NPFA uprush phenomenon, the collaborative research project. And on that project, I spent 11 years. And I have run about 1,800 tests and developed the model on the incident energy, the arcing current, and the protection boundary formula. It was adopted by the IEEE standard 1584, and it was published in 2018. So my current work is on the DC model side. And so what we try to basically do is try to enhance the estimation process and then come out another IEEE standard. Okay, so yes, the 1584 is it was published in 2018, and it's basically, okay, we need a DC uprush model. And then the other one is, okay, well, when you try to design a system, we always say safety by design. Okay, so for this particular case, the initiation point is at here. Okay, and then because when you design it, you try to create. So that is the basically walking distance. People are walking on this area, and it caused the fault. So then you try to create a certain area that become a weak point. So the arc basically transfer, instead of happening at here, they happen at here. Okay, so they transfer it over so it doesn't hurt people. So on this way here, that basically, from the personnel safety point of view, this is a very important design because it's a safety by design, and then you can reduce the potential danger or potential hazard to the personnel nearby. Okay, so yeah, this is the main body of the presentation. Here are some question answer from my previous presentation. People say, okay, how you define the efficiency on the battery? And then normally we consider it's a cycling, okay, from one SOC, state of charge to the, okay, from one status, and then charge to the, for example, if you basically, you charge the battery from SOC 1 to the SOC 2, and then discharge it back to the SOC 1. So the difference between the energy you charge and the energy you extract, then we consider this is your efficiency. Okay, so yes, at the different SOC, you may have a different efficiency. So you try to look at what is your overall efficiency. Then the battery cycle, okay, because yes, it's very, very common for us not to discharge the battery to the 0% and charge it back. Okay, so and even for the battery, we don't consider it's appropriate to fully discharge your battery too frequent. So we normally consider a depth of discharge is about 80%. You keep about 20% of the battery. So yeah, according to the Apple, it's basically you consider it if you charge discharge, and then, for example, if you charge to 100%, you use it up to the 40. You use 40% of the battery, then you charge back to the 100% and use another 60%. So you basically have it at 100%. We consider this is one battery cycle. Otherwise, that basically, okay, well, it's very confusion because, for example, if during the daytime, I put my cell phone on the charging stand and then charge it and I use it, does it consider one charge cycle? Okay, so this is the basically give a unified definition on the charging cycle. And so yes, we can measure. Okay, we can estimate the SOC and cycle life because now we try to look at it. For example, if you have an EV, they always ask you, okay, it's time to replace your battery when the capacity is less than 80%. And then, of course, some people also consider use those battery for the battery storage system because for the battery storage system, we don't have to worry about this. We have a less concern on the space constraint. And so you can do the SOC, you can do the cycle life, okay? And basically, okay, this is a very good technology already because if you use the electric vehicle, then they will tell you, okay, how many miles you can drive on your car. So that is basically give you the estimated state of charge, and then estimate how much energy that you can release. And of course, sometimes it really depends. Okay, so that also gives a so-called the anxiety. Okay, the basically driver's anxiety because yes, I tried one time on the electric vehicle and it's on uphill, so I drive about less than a miles, and then they tell me, okay, that it dropped about 3 miles on the available distance. So yeah, that basically, yeah, sometimes that causes confusion because the road condition and basically on the SOC estimation side. And then with battery, the performance in real time, yes. In the hybrid system, we try to look at the battery performance. You try to look at, sometimes you have depends on the chemical, depends on the battery, and then they are charge discharge rate. Okay, so that basically we look at the performance on the real time, and then because if you look at it, okay, sometimes you have to run through the testing because if you try to participate in the market, then they do require some performance requirement. Okay, for example, yeah, I know in ERCOT, if you try to serve as a Brexland unit, you do have some requirement, how much energy you have to produce and how fast you can get online. And the memory effect is, as I have mentioned, okay, for example, like a NiCad battery, if you don't fully discharge it and charge it back, if you charge 40% and then charge it back, if you discharge to the 40% and then charge it back, and then next time you discharge it 40% and charge it back for a period of time, the battery by itself will think, okay, they only have about 60% of the battery. So sometimes the NiCad battery, you have to fully discharge it. We call it a flush, that you have to flush the battery. For the lithium-ion battery, you don't have this kind of problem. So that's the reason why, okay, when you use your cell phone, you don't have to wait until you are fully discharged. You can charge it back, and the performance will not degrade. Okay, so then converter control for the inverter converter side. Okay, so you have two consideration. One is that you have a grid side converter, or you're going to have an off-grid. Okay, grid tie or off-grid converter. If you have a grid tie, then you have to follow the in the United States, we follow IEEE 1547 and the UL 1741. So that is basically, you have some safety concern, you have some requirement. If you have an upgrade, then that's a different story. Okay, so and a lot of time, a lot of upgrade inverter, they don't produce sine wave. They produce, okay, sometimes they just produce the square wave, they produce the quasi sine wave, or produce this pure sine wave. So the THD has some constraint over there. So and then the basically, okay, well, you should follow all the regulation, because sometimes the battery energy storage system considered as a DER, then you follow the DER regulation. Okay, so yes, the battery storage can be used as an independent or an upgrade. So that is basically, and then on that way, then what you have to consider, how are you going to charge the battery? Okay, for example, people can use a diesel, like in the remote telecommunication tower, and then they have a hybrid generation, hybrid system. And I have seen one, they put in the fuel cell, they put in the photovoltaic, they put in the battery storage, and they put in the wind turbine. And then on that way, so according to the company, before they put in a hybrid system, they use a diesel generator. So on that way, every week, they have to refuel the station. And after they put in the battery storage, they put in the photovoltaic, they have to refuel the diesel generator every 6 months. Okay, so this is the cost saving. And then what is the EDLC? Is the electrochemical double layer capacitor. Sometimes we call it the super capacitor. Okay, so is it possible to store alternative current without converting into the DC? Yes. Okay, you can use a frag wheel, you can use MG set, you can use a pump of the compressed air. Okay, so there are some different technology, energy storage technology. Okay, so instead of just using a chemical one. Okay, so that this is basically depends how you store it. And what battery is better charging the discharge curve? Okay, well, that depends on, again, it depends on your application. And lithium-ion battery, okay, they maintain the voltage pretty well. Okay, so if you look at the voltage output for the traditional battery, the lead-acid battery, the charging, when it discharge, the voltage drop. For the lithium-ion battery, the voltage doesn't drop significantly. So on that way, yes, your BMS or the detection system should be very good, because on that way, then it will be difficult to detect how much battery or how much the energy is remained in the battery. Okay, so in the future, yes, it's possible to replace the renewable energy and battery storage to replace the traditional generation. Okay, but yes, it's basically it's a technology, it's a variable space, and the bottom line is the cost. Okay, and so they can do it for the voltage and VAR control. Okay, so for example, in the power electronics world, historically for the power electronics, we do the grid following. Okay, so we don't try to control the voltage and frequency of the system. But once you get into the microgrid, or you try to do, and the power electronics getting bigger, then we try to do the grid forming. If you try to do the grid forming, then you have to do the volt control, you have to do the frequency control. So it really depends on the size you have, and depends on the application, depends on the ancillary service you try to participate. And yes, there's a basically, okay, well, they do have a large scale battery storage system, and again, the feasibility for that one is where are you going to, what kinds of service you're going to provide, and what is the market, because when they install the system, in addition to, unless you basically still a traditional regulated utility system, otherwise you always on the main purpose, when you try to do the battery storage installation, you try to improve the reliability of the system. You also try to make money come out of it. Okay. So compressed air, then the other one is a fry wheel, can also be an option, because the fry wheel, yes, they do have some improvement, some application in the fry wheel. You can put in the fry wheel in the semi vacuum chamber, and they use electromagnetic floating. Okay, so to reduce the friction loss. And or you basically use a very simple one, like a regeneration system on a train. Then on that one, you don't need a very sophisticated system. It really depends on the application. And then for the BMS, okay, so basically the battery is a very dedicated equipment. You have to do the proper protection. You try to make sure they don't operate beyond their boundary. So that is the main purpose of the BMS. And for the solar, and then it depends on your application. If you try to just store it, you try to do the regulation, okay, then that's a different story. If you just try to store it and use it later, then that basically you don't require a very sophisticated technology, okay. And so then when we look at it, okay, we call it a C-rate charging, okay. So normally we refer the high C charging or a trickle charging or a low C charging. Okay, so typical 1C, when we look at it, so if I have a battery, I'm doing a 1C charging or 1C discharge. It's 1 hour. Okay, the capacity of the battery, and then they basically, it would take me 1 hour to charge it. We call it a 1C charging. It takes me 1 hour to discharge it, 1C discharge. Okay, and so normally high C charging. So for example, some of the EV, they tell you, okay, 20 minutes, you can fully discharge, or 20 minutes, you can have a 50%. Okay, so on that way, in other words, then you try to look at it, it's okay, well, now, for example, if I tell you 20 minutes, you can have a fully discharge, then that's a 3C charging. 3C charging depends on the chemical of the battery, that can be damaging. Okay, yeah, I have a colleague in the lab, then he does the 3C charging on the lithium battery, above 200 charge cycle, the battery is out. Okay, so on that way, then basically what we try to look at it is, okay, well, it's a trade-off, and this is also a very active research area. How can we have a battery that can afford a high C charging? Because the high C charging normally is going to create a temperature rise, and also create a molecular swelling that basically damage the internal cell structure. Okay, so the battery storage, that basically, and then the other one is, okay, if you use the power in the power inverter side, then you try to look at the inertia of the system. You also try to look at the short circuit contribution. Okay, as you know, a lot of time when we try to look at it in the power system protection, we are looking for the short circuit current. And yeah, some of you may have done some so-called weak system study. Okay, the weak system is when you have a short circuit, you don't have enough short circuit contribution, and then basically you have a hard time to do the system protection because it's very difficult to do fault detection and isolation. So the protection side, so this is basically it's a very comprehensive study. You also, and then the other one is the power electronics, unless you do the virtual inertia. Otherwise, okay, their inertia is relatively small. and then that basically the frequency change will be fast. Okay, so if the battery has a low energy density and high efficiency, can it be used in an EV? Well, the answer is that depends. Okay, because how far you're going to drive and how heavy you have to carry the battery. Okay, and yes, we already use AI in the BMS because that is, if you look at the Tesla, it's basically they use the 18650 battery. Okay, and how are you going to? And every battery has a different performance. How can you rearrange the battery and put in the battery array, because you need the parallel and the series of the battery, and then make sure they perform well so they can last longer. And then it's basically, okay, the battery energy storage take part in the market activity. Yes, like in the ERCA fast response reserve and the PJM mileage. Okay, so thermal energy storage or mechanical energy storage. Well, that depends on your application and depends on it's always there's no silver bullet on the battery storage system. So it depends on your application. So a lot of time, it depends on your application. Okay, with that concludes my presentation. It lasts a little bit longer than I expected. Okay, but well, thank you very much for your patience, and I'm ready for any question.
Hi, Dr. Yes, we have a question here from Dr. Chi. He's asking, is the charging C and the discharging C of the battery is going to be the same? Asking about the design charging/discharging capacity.
Yeah, that basically the basic what we try to look at it is, okay, well, you always try to look at the charging C is 1 times. And it's basically 1 hour. Yes, it's approximately 1 hour. It's not what you try to look at it is, okay, you charge the battery 1 hour, then it's going to take a little bit longer than 1 hour. Okay, for example, in the Tesla one, you can see that is a proper design. It's 100 megawatt. 129 megawatt hour. So they on purposely reduce it less than 1 C to protect the battery.
Okay, thank you, sir. Is there any more questions? Because we asked participants to post their questions in the chat, but so far there's only 1 question from Dr. Chi. That was okay. Idea of posting the previous questions. I think it has answered a lot of the participants' questions. Another question is asking, is the lithium ion batteries raw material abundantly available?
Well, this is a good question, because it's basically, okay, the lithium ion battery, you see a lot of the basic discussion that China has a lot of rare earth material, the lithium, is that right? So they try to hold it for the market. But yes, the lithium by itself, you can have a lot, but how to extract it, it basically depends on the cost and the technology improvement. And also in the future, can we recycle those lithium material? And the other one is, okay, on the safety side, because several days ago, I read an article on the safety, and there's a car accident happened. It's a Tesla, the car accident in California. And so the firefighter, they basically come in, try to clean up, and it took them about 6 hours to clear it up because of the battery and also because of the discharge. And then sometimes the damage on the battery, then they cause the discharge and then cause the safety hazard. So yes, this is some area that requires some research, because fortunately that happened in California and not too far away from Tesla of the manufacturer. So they send their crew out to help the first responder. So safety is a very, very important part when you try to deploy the battery storage technology.
Thank you. Another question, it says, what's the application of hybrid energy storage like battery and plus supercapacitor?
Okay, so it's basically you try to coordinate because sometimes the system requirement. When you try to do the fast charging, that you always create a stress to the battery by itself. So if you can use a supercapacitor to fill in the first response, because the supercapacitor can do a very fast charging, discharging, and then so you coordinate it, so become a hybrid one. And actually, the other application you try to look at it is, I did some research on this part, is, for example, a wind generation. And the wind variation by itself, you have some high frequency variation, you have some low frequency variation. So in our research that we have used the wavelet to basically decompose the waveform, the variation. So for the high frequency variation, then you can use the supercapacitor to cover that part. For the low frequency, higher energy part, then you can use other technology. So on that way, you can basically, you don't have to use, it's not a one size fits all, and you can optimize your cost and maintain the performance.
Okay. Another question is from IR Lee. He's asking, some of the battery manufacturers mention charging of battery at 0.2 C with 1000 cycle. Is it common to have tick spec as such low C?
Well, no, it's basically, this is for their own protection. Okay, because normally, okay, I had done some study on the battery system on the internal structure, because if you try to increase the capacity of the battery, you need to increase just like the capacity, you need to increase the contact size. So a lot of technology, for example, some technology use a carbon nanotube. Okay, on that way you will be able to increase the surface. But if you have a molecular swelling, then you're going to break the carbon nanotube. And so this is the thermal transfer issue. If you use high C charging, then the temperature rise will be increased. And sometimes in the intermediates, the molecular swell. So it's going to break the carbon nanotube and then reduce the capacity. All right. So slow charging is always good for the battery. Okay. So that basically we call it the trickle charge. Okay. And if you look at this one here, if you put in a battery, if you put in 0.2 C over there, you need 5 hours to charge the battery, at least 5 hours to charge the battery. Okay, so for the typical traditional electric vehicle, we always use like in a level 1 charging, we are talking about 1 kilowatt. And then that take you about 14 to 18 hours to charge the battery. Okay, but then it's basically, it's good for battery, but it's not good for the user. Is that right? You have to charge 14, 18 hours and use it for 2-3 hours.
Okay. Prof, before I proceed, may I know how much time would you be giving to Q&A? Like another 5-10 minutes questions, because I think they're
that'll be fine.
Okay, yeah. Sure. There's another question is asking, is there any standard threshold of the charging discharging rate of a battery to be considered fast charging battery? We saw fast charging patents stating 2C and some 5 to 10C.
Okay, so it's basically normally if you go beyond 1C, we consider it's fast charging. Okay, and so if you look at it in the United States, the charging, EV charging, we have a level 1 charging, level 2 charging, and level 3 charging. And currently, level 1 has a standard. Okay, it's 120 volt. If you have a 20 amps, panel, you can charge up to 16 amps. If you have a 15 amp panel, you can charge to up to 12 amps. So this is, you can do it. It's basically, you are looking at about 2 kilowatt. Okay, and it's going to take a long time. So it's basically, it's a home charging. It's just like your regular large appliances. Okay, it's about the size as an air conditioner. Then you get into the level 2 charging. Level 2 charging is also can be a home charging. Okay, because on that one, because in most of the house in the United States, people has a utility room for the dryer. Then that come in with a 208. Or in other part of the country, in Malaysia, you have a 220 volt. Okay, so on that one, the charging time is about 4 to 8 hours. Then the level 3 is a fast charging, consider fast charging. So like in Tesla, they will tell you, okay, it's a 20 minutes, you can have a 50% charging. Okay, so but if you consider 20 minutes, 50%, and the battery, but then you also have to look at it. Okay, your charging port, because for example, if the Tesla it's a 70 kilowatt hour battery, 50% is 35 kilowatt hour, 20%. So the charging port, consider the efficiency, then that you have to put in. Okay, you have to put in the charging port about 120 kilowatt charging port, and in the distribution system that become a big load. So you have to look at it whether your distribution system can handle it or not. It's not just the car by itself. And currently, there's no specific standard. People are working on that one because you try to look at it. Okay, for the level 3 charging, people are looking at the beginning they put in a 380 volt. Now in the US we're looking for 500 volt, and then if you look at it over there, 500 volt, then it basically, if you have that voltage next to the person, when you do the charging, you are next to a people, then the safety become a very major issue. So it basically, they have some pros and cons over there.
Okay, thank you. There's another question from Siva. He's asking about how the technology heading towards ampere hour versus weight of the battery.
Okay, so the battery by itself, okay, if you look at the current mature technology, it's about 200 watt hour per kilogram. Okay, and yes, some technologies try to move it. You try to have it. Okay, I have seen some go up to about 300 watt hour per kilogram. And so when you try to look at it, okay, so that is, if you can do your own math. How many kilograms of battery if you try to drive 300 kilometers? Okay, so that is a 700 kilogram of battery that you have to put into the car in order to drive it. So that's always we are shooting for the high energy density battery. So on that way you can carry less weight and with more cargo space or passenger space, and then drive a long distance. So because this is basically you try to look at the energy density side. But of course, you always have some trade-off, because the higher the energy density, the higher the external protection required. So that will increase the space. And eventually it's going to reach to the balance point, just like for the generator. Normally we have a generator over there, and for the basically we know if we increase the voltage, we can reduce the current. Is that right? So you can reduce the copper. But when you increase the voltage, you have to increase the insulation. So that's the reason why most of the generator we have, it's even we know, okay, yeah, for the transmission line, we have 1,000 kV transmission line. But if you look at the generator, we only have, most of the generator is about 13.8 kV to about 35 kV. We don't go high voltage.
Thank you. Another question is asking how soon will the lead acid and nickel cadmium battery phase out and be replaced with lithium ion batteries?
Well, this is depends on the cost, depends on the technology, and yes, you see some basically, okay, well, the lithium ion battery, and it's light, it's a high efficiency, but well, that depends on the technology and depends on the cost. Just like the people always say, okay, well, when can we replace all the renewable energy? We replace the traditional generation with the renewable energy. It's also, again, it's the cost and technology and the maturity.
Okay. Another question is from Alex. Is it feasible to introduce supercapacitor to mitigate power quality issues such as voltage sag?
It's yes. Okay. And it depends on the as I say, okay, when I look at the power quality part, it's what kind of problem you try to solve and how long it will last. Okay. For example, if you have to calculate the capacity. For example, if you try to start a motor and then the voltage sag is about 3 seconds, is that right? Then you basically know what kinds of capacitor you need. And then the other one is, okay, well, if you try to look at some operation, the sag is just a couple cycle. Then that's a different application. Then you try to look at what is your target of application. And supercapacitor can respond very fast. It depends on your power electron detection, because when you try to do the sag mitigation, you try to detect the sag, you try to detect the amount of sag. So that is another set of the technology that you have to investigate.
Okay, thank you. I think we have reached our last question. Is asking for hybrid energy storage. Does it need to have specific converter to cover for the high power frequency and low power frequency?
No, you can use a separate one. Yeah, you basically, a lot of time you don't combine them together. You basically, a lot of time you can have it separate, because even we say it's a hybrid energy storage system, is basically you just consider, okay, you have a different energy storage system in the pack. Yes, you can use one controller, but when you use one controller, then that is basically it's basically the same thing. Separate controller, it's on the economic side. And my experience is, okay, use a separate one is better, because you don't put all egg in one basket.
Okay, I think that's all. Thank you very much, Prof. Lee. Just to let you know, if you look at the chat, there are a lot of people thanking you, and I think some of your former students are here. So thank you for the great session that you have shared with us. Thank you all the participants for attending this session. Thank you, Dr. Gobe, for being here. Dr. Sia Chun Lim, who have actually, thank you. You have connected me to the Prof. Lee. Dr. Gobe, any last question, any last statement from your side?
Thank you, Prof. Lee from MMU, Multimedia University. Thank you very much. So keep in touch.
Okay. Yeah, I was external examiner for six years, and then I conclude my service. And as I say, okay, well, I really encourage you to establish the IAS student branch chapter, because it's on that way that basically, okay, well, we do have a lot of resource to support the student activity.
Okay, we'll look into it definitely.
Yeah, we can maybe form a joint one with BESS.
Yes.
Can we do that? Can we have a joint?
Yeah, you can have a joint PES, IS pair. Actually, some university does that.
Yes.
They have a joint student branch chapter, PES, IAS, and the PEL, Power Electronics. So, yeah, it's possible.
Right. We'll look into it, Prof. Definitely.
Okay.
Thank you, Prof. Thank you
Thank
very
you.
much.
Thank you,
All
everyone.
right. So, thank you, everyone, for listening. And then, yes, yeah, in the first page, it has my email address. So, if you have any question, you can shoot me an email. And then, so then for some of you, it's night. So have a nice night.
Thank you, and have a nice, good night to everyone, and have a good day. I think you just started your day.
Okay. All right.
Thank you very much, sir. Have a good night. Have a good day.
You too. All right.
Okay, bye. Bye, everyone.
Okay. Bye.